If you are a sannyasi, nobody will give you bhik.
Correct.
Home person becomes sannyasi.
डॉक्टर निधि शुरू करें.
Namaste and good evening, everyone. Welcome to the Silver Jubilee session of the Tuesday lecture series presented by Vigyan Prasar for the Vigyan Prasar Network of Science Club. So, first and foremost, I would like to say a big thank you to all our VIPNet Club members whose continued support and response to the series keep us motivated so that we have reached our 25th lecture. I am Dr. Nidhi Srivastava, Project Scientist for Vigyan Prasar, and your moderator welcomes you all. It's my privilege to welcome the esteemed panelist of today's session, Dr. Ayan Datta, Professor, School of Chemical Sciences, Indian Association for the Cultivation of Science, Kolkata, Dr. Nakul Parashar, Director, Vigyan Prasar, Shri Sachin Narvadia, Scientist, Vigyan Prasar, and Mr. Vipin Singh Rawat from the VIPNet team of Vigyan Prasar. I also welcome all the club members who have joined us for this session today through YouTube. Thank you everyone for giving time for this session. Almost 100 years ago in 1916, the American chemist Gilbert Lewis proposed that the chemical bonds arises from the sharing pairs of electrons between the atoms. It enables scientists to take the 100 plus elements of periodic table to combine them in the myriad ways to form chemical compounds and their materials. Further incorporation of the principle of quantum mechanics in the chemistry led to the foundation of chemical bonding as a robust principle. However, new experimental results indicate that structure and reactivity of several molecules now require consideration of more refined concepts of chemical bonding. These include cases for the quadrupole bonding in carbon, concept of pH for few molecules, etc. In today's lecture, our expert will explain few such examples and some modern approaches to understand the bonding and reactivity of such molecules. The title of today's lecture is Chemical Bonding, 100 years and still looking for the surprises. The speaker of today's talk is Dr. Ayan Datta, Professor, School of Chemical Sciences, Indian Association for Cultivation of Sciences, Kolkata. The talk will be as usual of 40 to 50 minutes, followed by interaction session. I appeal to all the viewers. If you have any queries or doubt, you can type it in the comment section of the YouTube box and we will take your questions once the session is over. Now, to begin, I would like to invite our director, Dr. Nakul Parashar sir, for the welcome remarks, and I also request sir to please introduce our today's expert, Dr. Ayan Datta. Nakul sir.
नमस्कार. मुझे सबसे सर्वप्रथम प्रोफेसर अयन दत्ता का इस 25th लेक्चर जो आज हमारे विपनेट क्लब का जो हर मंगलवार को जो हम विपनेट लेक्चर करते हैं, जिसके अंदर हमारे पास बहुत विशिष्ट व्यक्ति हमारे साथ जुड़ते हैं जो अपने क्षेत्र में जिनको किसी परिचय की आवश्यकता नहीं होती है. और आज के लेक्चर सीरीज में हमारे साथ प्रोफेसर अयन दत्ता ने हमारा आमंत्रण स्वीकार किया. सर, आपका बहुत बहुत धन्यवाद. दिल की गहराइयों से मैं आपका अभिनंदन और आपको साधुवाद देना चाहूँगा इस बात के लिए कि आपने अपने व्यस्ततम क्षणों में समय निकालकर हमारे लिए आज इस व्याख्यान को देने का जो हमारा प्रस्ताव था उसको आपने स्वीकार किया. हम धन्य हुए, अहोभाग्य हमारा. और हमारी चेष्टा रहेगी कि हम इस लेक्चर से बहुत कुछ हमें सीखने को, समझने को मिलेगा और हमारे खासकर हमारे विपनेट क्लब के जो 2500-2400 से ज़्यादा क्लब मेंबर्स हैं वो से लाभान्वित होंगे. मुझे ये आपके साथ साझा करते हुए अत्यंत हर्ष हो रहा है कि कल हमने 50 और स्कूलों को अपने साथ जोड़ा. दक्षिणी दिल्ली नगर निगम के 50 स्कूल और हमारे साथ जुड़े और अगले हफ्ते हमारे साथ 50 और स्कूल जुड़ रहे हैं, जिससे हमारी संख्या लगातार तेजी से आगे बढ़ रही है. और इस सब के पीछे मेरे कर्मठ सहयोगी एवं मित्र डॉक्टर अरविंद रानाडे का ये प्रयास, उनकी मेहनत, उनका अथक प्रयास यही रंग ला रहा है. ये जो हम आज हर मंगलवार को जो शाम 4 बजे इस व्याख्यान माला की जो हमने कड़ी शुरुआत की, वो डॉक्टर अरविंद रानाडे का ब्रेन चाइल्ड है. डॉक्टर अरविंद रानाडे की बहुत सारी खूबियों में एक खूबी है कि वो बहुत सारे प्रोग्राम्स को बहुत अच्छे से लीड करते हैं, बहुत अच्छे से एग्जीक्यूट करते हैं. और उसका जीता जागता उदाहरण है IISF 2019 जो कलकत्ता में उन्होंने उनके नेतृत्व में हम सब ने मिलके किया था, और जिसके चलते इस साल 2020 का जब IISF शुरू हुआ तो इस बार की जो जिम्मेदारी, जैसा कि हर साल एक नए ऑर्गेनाइजेशन को मिलती है, तो इस साल CSIR को जब ये रिस्पॉन्सिबिलिटी मिली तो उन्होंने निस्टैट्स, जो उनका नेशनल इंस्टीट्यूट फॉर साइंस एंड टेक्नोलॉजी डेवलपमेंट स्टडीज़ का जो संस्थान है, उसको रिस्पॉन्सिबिलिटी दी। तो उसमें अंत में यही हुआ कि कहाँ है अरविंद जी, बुलाओ भाई उनको, और वही अब आगे इसको लेके चलेंगे। तो आज वो वहाँ व्यस्त हैं, उनके साथ सचिन जी भी उनके साथ काफ़ी व्यस्त थे, किंतु आज हमने कहा ये एक ऐसा कार्यक्रम है, दो में से एक को तो यहाँ रहना पड़ेगा। तो राष्ट्र के हित में ये निश्चय हुआ कि बड़ा कार्यक्रम है, लिहाजा अरविंद जी वहाँ रहेंगे, सचिन जी यहाँ रहेंगे। तो राम को वहाँ बेच के लक्ष्मण को हमने अपने पास रखा है यहाँ। तो आज उम्मीद है कि हमारा ये लेक्चर, जो स्वर्ण जयंती का जो ये स्वर्ण नहीं, रजत का जो ये हमारा लेक्चर है, ये बहुत अच्छा होगा। और इसके लिए हमें सबसे खुशी इस बात की है कि इसके लिए आज हमारे साथ प्रोफेसर अयन दत्ता हैं, जिनके साथ हमने मिलके पूर्व में बहुत सारे कार्यक्रम किए हैं, और कलकत्ता में विशेषकर हमने विवेकानंद विज्ञान जो हमारी वो संस्था है, VVM मंच है, उसके साथ उनके साथ हमने बहुत काम किया है। Professor Ayan Datta is a person, is not because he is here with us, but a person who is very down to earth, understands science, and is an effective science communicator. Dr. Ayan Datta is currently serving as the professor at the School of Chemical Sciences and at the Indian Association for Cultivation of Sciences in Calcutta. His research work focuses on a unified understanding of phenomena at various length and time scales using techniques based on ab initio and extended quantum mechanical methods. His group has contributed towards two-dimensional systems like silicon and graphene analogs and provided a relationship between electronic structure and the ground state properties. Professor Datta has been awarded with the distinguished, and he is the distinguished SERB Investigator Award in 2019. He has also been awarded the INSA Young Scientist Award and has been a Young Associate of the Indian Academy of Sciences in 2010. Professor Datta has published more than 180 scientific papers in peer-reviewed journals, and according to Stanford University survey of 2020, Dr. Datta is within top 2 scientists in the world of chemical physics. We are very proud to have you here, sir, and I'm sure our gathering would certainly benefit from your esteemed lecture today. I know we are all very eager to hear him, so I will step out between the audience and you, sir, so that you may proceed with your lecture that we are eagerly waiting to hear from. Thank you once again, sir, for having accepted our invitation. It's indeed a pleasure and privilege, honor to have you with us. Thank you so much, sir. We remain indebted. And with this, I would now hand over for the proceedings of this whole lecture series to Dr. Nidhi Srivastava. Dr. Nidhi Srivastava.
Thank you so much, sir, for your kind motivating words. Now I invite Professor Ayan Datta, sir, to please begin your presentation, sir.
So, first of all, am I audible?
Yes,
Yes,
yes.
sir.
First of all, let me start by thanking the director, Dr. Nakul Parashar, for these wonderful and kind words. He's an extremely busy man, but he's an extremely polite man, a very nice person to work with. I have worked with him. I'm sure Vigyan Prasad works with him, and he. Let me also add to my own personal anecdotes. He's an atypical director, even though he's a director. But the way he talks to his employees, and particularly this is something which all of us need to learn, that one should not execute the power, and then one should the respect and the dignity should come from within the employees. So this is something all of us need to learn from Dr. Nakul Parashar, and he can take everybody together. He takes people together. And I also thank Sri Arvind Ranade ji, who has also been a kind of a stone, I mean, stepping stone for many people to grow up, and particularly science outreach program. So I think this is the teamwork of Nakul Parashar ji and Arvind ji, Sachin ji, and Nidhi ji, who are making Vigyan Prasar a big success. And we are all looking forward to this new innovation, which is the India International Science Festival of 2020, which will be on the virtual platform. So let us see how the virtual platform becomes a reality. And I wish Team Vigyan Prasad a very happy and successful time ahead. And as we know, and this, I mean, let me also give a little bit of introduction. This India International Science Festival this year is going to be held from 22nd to 25th of December, and both the dates are very important in the Indian science landscape of this country. 22nd November, 22nd December is the birth anniversary of Srinivasan Ramanujan, one of the greatest genius. And it is very sad, and I should say this: the I mean, the first successful movie on Srinivasa Ramanujan has not been made by an Indian movie. It has been made by an Hollywood movie. Very sad. We talk about people respecting our people, but we don't do it. It has been a Hollywood. It has been a major motion picture, A Man Who Knew Infinity. The movie has been made by Hollywood. And 25th December, we all know, is our beloved Atal Bihari Vajpayee's birthday. The man who coined the term Jai Jawan, Jai Jawan, Jai Kisan, and Jai Vigyan to celebrate the testing of the testing of the peaceful nuclear device, which made India self-reliant and self-confident in science and in our national narrative. So I thank and wish Team Vigyan Prasad a very successful time. Thank you very much. So let me begin my scientific deliberations. So I think I should also thank Dr. Nidhi Srivastava for a wonderful introduction. I mean, the kind of introduction which she has given, she actually set a wonderful platform, and I will try to use that platform to build upon a story. And I would like this deliberations to be as much informal as we want, because remember, this is Vigyan Prasad. We will learn. The reason why I always accept to deliver a lecture is because I also get to learn new views, and that is very important. And that goes all around my career in try to define my own models and my own theories. So there is also a vested interest, because when I talk to students, students ask me questions, and I go back to my research lab, try to ask these questions in a different way, try to think a little bit more on it, and then try to come up with a theory which becomes more internationally acceptable. So remember, teaching is not a one-sided affair. It was never a one-sided affair. Teaching is a two-sided affair. So it's not that the teacher teaches and the student listens. No, the student also teaches the teacher. And I will give you examples where the students have asked questions in my classes. I have gone back to my laboratory, and then I have done research on that. And those have become very important research problems in the landscape of modern science. So I will start with that. So let me share my screen. So what we are telling, so if you are a chemist, you know about chemical bonding. Now you cannot be, I mean, everybody knows about a chemical bond. So what is a chemical bond? We'll come back to it. So what we are trying to look at, we'll try to look at something which is very simple and obvious, and we'll try to understand it from very simple questions, and we'll raise simple questions and try to see whether we understand it. And as we go around, we will see that many of the things which we assume as obvious are not really that obvious when we come to think about it. Okay, so just to give you a kind of a little detour, so I come from the eastern part of the country, which is called the Indian Association for the Cultivation of Science, which is the oldest research institute in India. In fact, which is the oldest research institute in Asia. It was founded by Dr. Mahendralal Sarkar, the first MD doctor of India, and it has had faculty like C.V. Raman, Meghnad Saha, Satyendranath Bose, and K.S. Krishnan. By the way, Dr. Mahendralal Sarkar was also a very famous doctor, and one of his very important clients was Sri Ramakrishna Paramahansa. Okay, so now of course this Indian Association for Cultivation of Science is also offers BS and MS degrees along with PhD. So, and we take students based on a kind of a national level selection exam after written exam and interviews, and we give stipends to students. So many of the students can actually look at the website of ISAs and can apply for a PhD or a BSMS degrees and we have all modern facilities which you can think of, with the highest form of cutting edge research. Now, the point which I'm trying to tell you, and this has hardly been mentioned, when you look at history, how do you name history? How do you classify history? In fact, if you look at history, history is actually classified based on chemistry. People don't realize it. One of the very first, when you look at history, you say copper age. You talk about bronze age. You talk about iron age. And then you keep on talking about civilizations and their age. But have you ever worried why they are called copper age, bronze age, iron age, the Renaissance, industrial revolution? Why it is called industrial revolution? Because whenever we are talking about this classification of history, we are actually talking about this big jump in the understanding of the human mind. For example, when we talk about copper age, we actually talk about that the people or the human civilization at that moment of time were using copper as the metal. And why they were using copper as the metal? Because they were using technology, because that is was the technology available to the mankind, that was the available way in which they could reduce copper oxide ores to metallic copper. For example, people of the copper age did not know how to use bronze. Because, for example, when you need bronze, you need copper. You need copper, zinc, and tin to make an alloy. But people of the copper age did not know how to make bronze. So the people, so the understanding, the civilization, the culture was restricted to a particular metal, and that metal defined the the level of understanding of the civilization. So when you come to iron, and in fact, iron is one of the very important metals. In fact, that changed the landscape of human civilization. So when we talk about Iron Age, we mean that at that time, mankind learned how to extract iron. And we know what is the ore of iron is called hematite, which is an iron oxide. And to reduce iron oxide, you have to use much higher temperature. So the reason why the people of copper age, well, it's not that iron was not available to the people of the copper age. It was realized that it was an iron ore, but they had no technology. In other words, they did not know how to extract iron metal from an iron oxide, because that required a higher temperature. As a result, to get a higher temperature, you need a better technology. So control of the temperature actually produced a control on the metal and the civilization therefore. Now, when we talk about industrial civilization or the industrial revolution, which is around late 17th century, late 18th century, 1750 onwards, what changed was the steam engine. A single important milestone changed the direction of the human civilization. Because once we knew how to use steam engine, we knew how to use machines. We knew how to use large scale production. So slowly what happened with industrial revolution was that you could do large scale production, you could reduce production, you could reduce the kind of the charges, the prices of the things crashed. As a result, there were big changes in the society. Indian civilization, sadly because of this, had to suffer this big problem, because coal, iron, and everything started to move out of India. And then India had to again re-import the processed thing. As a result, the Indian economy survived. And the reason why we had to go through all that was because we did not know how to use steam engine. So as a result, if there is a civilization or a country has to grow, that country has to grow based on technology. Very clear. And that technology will come from chemistry, because all across the human civilization, what was controlling the narrative of mankind was the availability of the chemical technology. Followed by this, we had this polymer revolution. Think about those old days when people used to wear clothes. Clothes used to be so expensive, very, very expensive. But then suddenly everybody could afford clothes, because then polymer came, polyester came, and Reliance Industry made. Reliance Industries in 1950s and 1980s changed the landscape. People could, common men, middle class people could afford 2 to 3 shirts. Women could afford 2 to 3 saris. This was unheard of. So as a result, that changed the sense of presentability of the Indian middle class. Very important. And why was it available? because the polyester which was produced by the Jamnagar plants by Reliance Petrochemical actually made India self-reliant. We did not need to import polyester and polymers from abroad. India did become polyester. So if you ask me, one of the greatest, in the 1980s, one of the greatest scientific, in terms of the impact to mankind, has been the polyester plants of Reliance. Great contribution to humanity. Because without this, India would always need to export clothes, cotton from Manchester, processed cotton from Manchester, and Indian had to, anything good had to be imported. But the first time that India could start to make manufacture clothes in India. Okay. Now, followed by this, what is the new technology which is happening now? The new technology which is happening is the nanotechnology, carbon nanotechnology. And we have to use this bus. We should not fall behind. We should not fall behind because today this for example, these chips in our mobile phones, the lithium-ion batteries, we are not producing a single lithium-ion battery in this country. Nowhere. We are all importing. Why? Because we have to become self-reliant. And to become self-reliant, we should know how to use the technology. So the point I am trying to make here is human civilization is controlled by the ability of mankind to use chemistry to its own benefit. If you are not able to use that benefit, we will end up becoming a kind of a supplier of manpower and no intellectual ability. The way India will become Atmanirbhar is by becoming Atmanirbhar in chemical sciences and chemical technology. Without this, there is no Atmanirbhar Bharat. I give you a few examples. Hydrogen is the lightest element in the periodic table. Incidentally, this is the most abundant molecule in the universe. 75% of all the universe is composed of hydrogen. In fact, it was discovered by Cavendish in 1766, long back. Now, hydrogen molecule is a very important molecule because hydrogen molecule is wonderful because when you burn hydrogen, and what happens when you burn hydrogen, you produce water, right? And water we know. And then when you burn hydrogen, you release a lot of energy. So as a result, instead of using the petrol which we import from Middle East countries by paying a lot of dollars. In fact, a large portion of the India's trade balance is imbalance rather, is because of the fact that we don't have much petrol. So we have to import from the Middle East countries. But if we, India, can use hydrogen as a fuel, how do we use hydrogen? You have to burn hydrogen, you will get energy. Of course, there are issues with that, and we'll come to it. We would be able to be self-reliant. Now, of course, we know that hydrogen is also a very important molecule because when you have hydrogen and when you have with oxygen, you have what is called water. And water is a very important liquid because water forms network and water forms what is called hydrogen bond. And hydrogen bond is all across our things. For example, the fact that I am different from you and you are different from your brother and your brother is different from your sister is largely because of the fact that my DNA, your DNA, and our and others' DNA differ from each other by small mutations. And those small mutations are caused by the fact that this DNA bases of each human being are arranged with respect to each other in the little different packing orientation of the strength of the hydrogen bonds. So as a result, you have various kinds of mutations, and as a result, what stabilizes the DNA in its structure is the hydrogen bond, and this hydrogen bond is weak, but that gives a lot of energy and stability and diversity to the molecules, which creates the basis for the genetic information across the society. For example, I give you an example. In fact, this is a very important data, and this is a data which we have from 1800s. Look at it. So what we have is the amount of carbon which is being emitted in the atmosphere. Why carbon is emitted? Because whenever we have fuels, we burn it. Any fuel, when you burn it, it produces carbon dioxide, and that carbon dioxide goes inside the atmosphere and it causes what is called the greenhouse effect. So what people have studied over a very large period of time, for example, from 1800 onwards, and what people have found that you can actually see that the emission of carbon, when we have, in fact, this is what happens right now in Delhi. because you have almost all smog around, because you have this sulfur dioxides and this all oxides and the carbon emission, which produces a large greenhouse effect, and then you feel like smoggish. And what happens that we have seen that just after 1950, when people started using very largely, when oil was discovered in the Middle East, people started using oil, and then that replaced coal. And as a result, you have seen very large enhancement in the carbon emission in the world. And this almost correlates with the increase in the global temperature. So as we have data from 1860 to 2000, where you see that the average global temperature keeps on increasing in average. So as a result, with time, you see the world is becoming more and more and more hotter. As a result, exactly correlating in the negative sense, as you are increasing the world temperature, you are seeing that your glaciers are melting. As a result, the glaciers on the Arctic and the Antarctica are reducing. As a result, with time, you will see many of the glaciers will melt, and particularly the coastal areas of India, like Kerala, West Bengal, Bombay, would see more and more floods, and you will see large and large kind of destructions. So, in fact, this is one aspect. The other aspect is the fact that not only does this petrol or diesel cause emission, global warming, it also is also very sensitive. For example, this is the price of oil over a period of 1947 to say 2008. You see, the prices of the oil has been really fluctuating, and it fluctuates whenever there is a world crisis. So as a result, not only as a result, our economy, in case we are not self-sufficient, we would be not be insulated by the large changes and the fluctuations in the prices of the petrol. As a result, we have to end up, otherwise we have to orient ourselves, our own national interest with respect to other global parameters. So ideally, India, not only in terms of our own scientific independence, but in terms of also to maintain our sustainability and criticality, we should be have our own sources of fuel, so that we don't need to depend on imported materials, because those important, if we start to import, for example, if when you had the Iran Iraq war, the prices of dollars just shooted up, and because the prices went shooted up, when you have the Kuwait war, the Gulf war in 1991, the prices shooted up. The India had to import at a much higher price. As a result, there was a credit crisis, and there was a huge problem in the Indian economy. So also to protect our economy, we need to be self. So what is the way out? One of the very easy ways out is to use hydrogen, and hydrogen is abundantly available in the earth. So what only thing which you need to know is the problem is hydrogen. It vigorously reacts with oxygen to produce energy, and it produces water, and water is harmless. Problem is that this energy is very vigorous. As a result, you cannot store hydrogen because it will be explosive. So the idea is to store hydrogen in a way in which you can actually this can become this can be this the hydrogen can be stored and released in a safe fashion. So now there is a lot of interest in materials like this metal organic frameworks, fullerenes, nanotubes, and nanorods, which can store a lot of hydrogen and which can release hydrogen in a very in a controllable fashion without creating combustions or explosions. So now there is all across the world there is an interest to generate this kind of buses and cars where instead of using petrol, you are using to use hydrogen, and that will make you completely independent of the import cycles of getting of buying oil from Middle East countries. One, and secondly, it will also save you from pollution, and this will also be good for the environment. The other important thing, which is something which we need to do in a very large way, is something which is, and this is something which all of you have removed, all of you should have realized. For example, 20 years back, have you ever thought of the size of a computer? This used to be so big. Now, with time, the size of the computers are becoming smaller. You see, now you can do on your smartphone things which you earlier 5 years back you could not even do. You could not even do on a very large computer. So as a result, people have found that there is something which is happening every 10 years. every 5 years to 10 years, the speed of the computers are becoming twice faster, faster and faster. And as they are becoming faster and faster, sizes of the computers are becoming small. In fact, this was predicted by a gentleman called Moore. He said, every 5 years, your computers, the size of your computer, the chip on the computer is going to become by half. So as a result, we have reached a limit where you can actually have molecules, a single molecule which can be used as a transistor. Now, this is one of the greatest discoveries where you can actually use a single molecule to to make a transistor where you will allow current to pass in one direction, whether when and while the current will be stopped or will be locked in the reverse direction. So there has been a large kind of things where we can use miniaturization of our knowledge. So as we go down and down with time, our computers, our memory, our smartphones are going to be smaller. As a result, you are soon going to limit where your sizes of the transistors are not going to be millimeters or centimeters, but they are going to be nanometers. By the way, what is a nanometer? So, in other words, a nanometer is something, for example, you might have heard of something called a Tata Nano car. So, a nano car is something of this dimension, and if you reduce by 10 to the power minus 9 times, you get what is called to the nano dimension. And of course, nano things are known. In fact, you would think of it. For example, the fact that, have you ever worried that how does a lizard climb the wall? Have you ever thought of it? How does a lizard climb the wall? People earlier days used to think that the lizard climbs the wall because there is some vacuum on its claws and then there is something like this. But people have done very high quality research and people have found out that the reason why lizard actually climbs the wall is because there are very small nanoscale fibers on its surfaces. So when it puts those surfaces on the walls, they form very weak interactions. These weak interactions are called van der Waal interactions, very weak. And these van der Waal interactions are enough to keep the weight of the lizard, and that is the way lizard climbs the wall. Incidentally, in India, we always knew this. Many of us know that in the late 17th century, Shivaji used to, Shivaji and his general Tanaji used to attack and win the forts of the Mughals using these trained lizards, and using those lizards, and people could climb the walls. In fact, the reason why this lizard climbs the wall is because of the fact that the claws of the lizards have very fine hairs which cause van der Waal interactions with the surface. Very important. So the question is how big, how big or how small is a nanoparticle? So one of the easy ways to understand a nanoparticle is, you have seen a football. So if you take a football and expand its size by 10 to the power 9 times, you will get an earth, the size of the earth. Whereas the same football, if you reduce that size by 10 to the power minus 9 times. So one is you are increasing the size by 10 to the power 9 times, you get an earth. And if you take a football, reduce its size by 10 to the power minus 9 times, you get what is called a nanomaterial, which is called fullerene. The fullerene is called buckyball because this is a molecule which is very symmetric. And this is, of course, nowadays being used very routinely in getting, this is, by the way, where do you get fullerenes? Fullerenes are produced when you have carbon suits. For example, when you put kajal in your eyes, the kajal largely contains fullerenes, nanomaterials, black nanomaterials. So what is the importance of these fullerenes? Fullerenes are extremely, they add strength to materials. So whenever nowadays all this, kind of things which need, for example, these rubber bands or the good quality rubber bands which you have, or things for the industrial rubber bands, they are blended with fullerenes to increase their mechanical strength, right? So the idea is, in fact, this nanomaterials was first discovered by a gentleman called Michael Faraday. Now, Michael Faraday is a very important person in both physics and chemistry because Michael Faraday, incidentally, also discovered electricity. He also discovered the laws of electrochemistry, and he also discovered what is called the laws of electrodynamics, right? So what happens? So what Michael Faraday did, you have gold and you start dividing it. And once you start to divide it, it becomes gold salts and which can be stabilized in the solution. And incidentally, what he found that these salts can be stabilized, and then depending on the size of those nanoparticles, they can have different colors. In fact, this phenomenon is what is called now known as quantum confinement, because depending on the size of the nanoparticles, you can have different colors. In fact, this is something which I always like to say. Michael Faraday discovered the first nanoparticle in the year 1857. Now, 1857 is a very important date in the context of India, and many of you know. So, what does 1857 stand for? Many of you, in fact, I have visited a lot of schools and colleges, and all of them say 1857 is the Sepoy Mutiny because of the fact that Indian history has been taught by British, and British has taught us how to write our own history. In fact, no Indian should ever call 1857 as the Sepoy Mutiny, and every Indian should call it as India's first war of independence. In fact, the first person to point out this was Veer Savarkarji, who wrote in his book. In fact, the book is titled "The Indian War of Independence of 1857." So when we say 1857, we should say the first Indian War of Independence, and one should not say a Sepoy Mutiny. The British historians or the historians paid by Britishers, and they were very intelligent people, with all due respect, very intelligent Indian people, very decorated scientists, historians, who have always said 1857 is the Sepoy Mutiny. Of course, it is a mutiny for them but it is independence for us because of the fact that our soldiers of all caste, all religion, all languages decided that they should have their own country. So, in other words, as Veer Savarkarji said, and all of you should read this book, has said that this should be the India's war of independence and not Sepoy Mutiny. So interestingly, Michael Faraday in 1857 said, in fact, Michael Faraday was called by the British finance minister. And then people were talking that, Michael Faraday has by the time already become very famous. So everybody is saying that Michael Faraday, you have discovered something. So the parliamentarians called him. And then the minister said, I hear that you have discovered something. And you said that you have discovered something called electricity. What good use is electricity for? What can I do with electricity? Then Michael Faraday told the British Minister of Finance that one day, Minister, you will be able to tax it. And this is exactly what all the governments in the world do now. All the governments in the world tax electricity. Why? Because of course you want to make sure that people don't waste electricity. So if you are using less electricity, you will be taxed less. Where if you are using large amount of electricity, you are running 5-6 ACs in your home, you will be charged more. So that is the power of the vision of science. The fact that in 1857 he did not know what you should do with nanotechnology or electricity, but he certainly knew that in it that these are very important technologies which can change the landscape of human mind. Interestingly, there is a very important discovery in the name of an Indian, which is Satyendranath Bose from India. And Satyendranath Bose had shown in 1924, he and Einstein together showed that you can have very unusual atoms. He did not know what are the atoms. He did not know what are the system. But he did predict that if you are able to quantize atoms, you would be able to get what is called a boson. And those boson, and you will get what is called Bose-Einstein condensation, in which all the particles will be confined to one electronic state or one photon state. In 1924, he did not know. Nobody knew that what will be the system which will show that. Followed by this, there have been several Nobel Prizes. In fact, there have been 5 Nobel Prizes just to prove that, which proved that Bose and Einstein was correct. For example, in 1995, the famous group at Colorado showed that you could condense atoms. Once you reduce temperature, you can put all the atoms in a single quantum state. What do you do with that? The answer is we don't know yet. We don't know yet what do you do with a boson. But the finding is this is a very important discovery, and I'm sure one fine day we would be able to find important applications for this fundamental quantum effect. Okay, so the other important thing which I thought that I will give you a few simple examples which many of you have been taught. For example, all of you know sodium chloride is ionic, and we know that ionic bonds are stronger than covalent bonds. And we will see some examples that how much of it do we really understand. For example, we see how do we understand the structure of sodium chloride. So typically we see that when you have a electropositive element and an electronegative element, you join them together as if the sodium is electropositive. So of course it would like to go to an octet configuration. So it loses an electron, it becomes sodium plus, which is an octet configuration. Whereas chlorine, which is highly electronegative element, wants to take the extra electron, and then chlorine becomes chloride, which also satisfies the octet configuration, and then both of them are stable and all of them form octet. Unfortunately, that is not the right picture, because if you look at it, the ionization energy of sodium is about 500 kilojoule per mole, whereas the electron affinity of chlorine is minus 350 kilocalorie per mole. In other words, if you take a sodium atom and a chlorine atom, you mix them together, that would be endothermic, because that the total sum of the energies will not add up. So what adds stability to the structure is the fact that when you take sodium and chlorine and then form the sodium chloride gas by this kind of a process, which is called the Hess's law, you will see what you get. The fact that what stabilizes it is what is called the lattice energy. The fact that you are able to put sodium opposite charges together brings in stability. In fact, this is what is called the Madelung constant, and it is the Madelung constant which is the presence of ordered charges, cations, ordered charges negative, and which, based on their simple electrostatic orientation, adds up stability to the solid. So the fact that sodium chloride solid is stable is not because it is just because the charges satisfy the octet rule. It is also because of the fact that they form ordered structure, and because of the ordered structure, the Coulomb forces get stabilized, which makes up the system stable. The same logic is also applicable for other solids like hydrogen fluoride. So hydrogen fluoride, if you can always think of having H plus and F minus. But hydrogen fluoride does not get stabilized as a solid, because hydrogen fluoride hydrogen ion is much smaller than that of fluoride. As a result, there is a lot of disorder in the structure, which causes the hydrogen ions to move across. As a result, you can think of that even at very low temperature, hydrogen fluoride gets melted and it forms disordered structures, something like hydrogen bonded liquids. So as a result, even though it does not form a solid, but it still maintains the ionicity, and because of this ionicity and the hydrogen bond, the structure gets stabilized. For example, the same logic is also applicable for other structures. For example, when you say that ammonium chloride, you would like to think of ammonium chloride as an ammonium ion and a chloride ion. Unfortunately, this is true. This is true in the solid. But when you have only few molecules, for example, when you have one ammonia and say one molecule of hydrogen chloride, it will of course not form a ammonium chloride, it will form a hydrogen bonded complex. But as you keep on adding more and more molecules inside, eventually when you will have Avogadro number of molecules, that individual ionic ions are individually stabilized by the overall lattice structure of the solid. So the point is, when we say that ionic structures are more stable than covalent structure, which is in general true, which is taught across all the textbooks, which is only in the limit when you have Avogadro number of atoms or molecules. For few atoms and molecules, or other words, when you have nanosystems, this is not stable. The other interesting thing which you all know, that for example, when you have an alcohol, so phenol and water, they mix. And as a result, but then how does a phenol and water mix? The fact that phenol and water mixes because a phenol molecule will form a hydrogen bond with itself, as well as with the hydrogen molecule or with the water molecule. So as you keep on adding more and more and more molecules of phenol and water together, they co-solvate each other, and after some time, they form a mixture. So as a result, because of this simple hydrogen bonding at the nanoscale limit, this is what stabilizes a phenol and a water system, right? Interestingly, we all are taught things like dissolves like, right? We say that a kind of ionic systems dissolve in water, and as organic solvents dissolve organic molecules, which is not true, because people have found that, in fact, there has been a lot of interesting work. For example, people have taught. For example, there is a very interesting article which says the world's smallest cup of water, in which you can see a single water molecule entering a small molecular cup, which is a kind of a calyxarine kind of thing. And the people ask this fundamental question: where the water molecule is, whether it is inside the cavity or the outside the cavity. And people have shown based on very simple things, simple calculations, that it depends on the nature of compensation of the interactions as well as the nature of attraction. So it is a competition between intramolecular hydrogen bonds and intermolecular hydrogen bonds. And this is very weak balance between intermolecular hydrogen bonds and the intramolecular hydrogen bond actually determines the state of the system. There are other effects, for example, Yan-Taylor effects, which also are important. And interestingly, in our textbooks in our high schools or even first year colleges, we teach Yan-Taylor effect, which is the distortion of high symmetry structures in the electronic states, in the degenerate electronic states. They are taught only in the context of inorganic compounds. However, there are large examples of Yan-Taylor distortions. For example, in organic molecules like cyclobutadiene, where you get to see the similar effects. So in other words, even in the organic molecules, you get to see such kind of a large effects. And you get large examples of Yan-Taylor distortions in all across organic chemistry. So, for example, this brings me to the last part of my lecture, which is like bonding. Chemical bonding as such is known. Chemical bonding is known for the last 100 years. And one of the classic work of this has been the work of Lewis. And it has been a wonderful wisdom on his part when he thought that, he always knew that atoms prefer octet configuration. So he assumed that maybe atoms are like cubes. Well, he did not have any good scientific reason to justify it. But the fact that you could, any atom with 8 electrons becomes stable, so he assumed that the electrons probably are arranged in a cube and the electrons are as far away from each other like the edges of a cube. So which perfectly satisfied it, which also perfectly explained why the noble gas elements are stable, because the for noble gas elements or the inert elements, you see the hydrogens, the electrons are further away from each other, and we know the electrons repel each other. So if the electrons are as far away from each other as in a cube, then you would be able to explain the stability. Of course, that also adds a wonderful thing, because now you can explain stability. You can form bonds. So now you can say that you can have a single bond when you have the two edges are shared. Then you will have a single bond because the two electrons are getting shared. You can also explain double bond when the faces are get shared, right? Because then you will have two electrons and those two electrons are shared. Wonderful logic. You could even explain half a bond, a molecule like H2 plus, where you have only the edge sharing. I mean, the cubes get sharing only with the edges. Problem which Lewis faced and which actually effectively overturned his theory of chemical bonding is the fact that he could not explain the structure of acetylene, because in that case you need to put 3 atoms together on the same phase. Now, of course, we know that atoms repel each other. So if atoms repel each other, how do you bring all 3 atoms on the same phase? Because when you have brought 3 atoms together on the same phase, then only you will form a triple bond. Unfortunately, Lewis, all with his brilliance, could not explain a formation of a triple bond. So as a result, the reason why I'm trying to bring in the point is chemical bonding is a very evolving topic. The fact that even Lewis, with his very brilliant mind, could not come up with a theory, a simple theory which could explain a triple bond. So as a result, you could explain a triple bond by forming things like this, but that would force you electrons on the same phase. As a result, electrons would repel each other. So of course, you can do that by assuming, in fact, this is what he even attributed, that probably if my dielectric constant is negative, then of course electrons can start to attract each other. So then he probably thought that atoms are negative dielectric constant materials, by which he could probably explain, but this explanation was wrong. The point which I'm trying to build is chemical bonding from the days of 1916, where it was first predicted by Lewis. It has been evolving. In fact, we have also been looking at examples where you can have chemical bonds where you really put atoms together. You can really force atom by applying pressure, and in which those two atoms can come closer. For example, you can have examples where you can have two hydrogen atoms which are rather close to each other, and you push them further closer down, and then you see that the hydrogens would start to attract each other. So these are very constrained iron chambers. These are chambers like which are really constrained, where you can have very important reactivity under pressure. So finally, for example, there has been a lot of debate over a period of time for even a simple molecule like C2. For example, if you look at the bond order of C2, and any high school student knows this, the bond order of C2 is 2, which assumes that you have the electrons in the pi orbitals, and as a result, you will have a bond order of 2. Unfortunately, if you look at it, you can always have a valence bond structure, or you can have a resonance structure, where you can see that you can have 3 of the bonds around like this, and the 2 inverted bonds are connected with kind of an inverted bond. So people thought that you can have inverted bonds which are connecting them. And as a result, people found that, in fact, there have been very old work. This is another Nobel laureate, Haris Mulliken. He suggested that probably a C2 molecule has a bond order of 4. And then people have found examples in which people could put molecules, a simple molecule like C2, where people thought by default that the molecule of C2 would have a bond order of 2, maybe the bond order is much higher than. So in other words, even the simple molecular orbital theory, which is taught to the students for a simple molecule like carbon, that needs a revision. In fact, we all know this is an example of a molecule like sodium chloride. Sodium chloride is stable, but under pressure, sodium chloride converts its phase to something like sodium trichloride, NaCl3, which is very unusual because we know that sodium has a valency of +1, whereas a chlorine has a valency of -3. But then how would you form a compound like sodium trichloride? The answer is under pressure, the electrons get shared, and as a result, sodium chloride is no longer an ionic solid, but it almost behaves like a covalent solid. So the point is, as more and more new discoveries are made, more and more new phases of systems are being known, many of the old theories, the 100-year-old theories, would require changes. For example, I give you an example. This is known to all of us. This is the IUPAC accepted periodic table of elements. But we see that even this 150-year-old periodic table needs a revision. For example, look at it. These two elements, lutetium and lawrencium, we always put them as F block elements. Unfortunately, there has been an article a few years back which said that probably the fact that this lutetium and lawrencium, the lanthanide and the actinide series, the last element, probably should not be here and probably should be transferred somewhere here. And how do you know that? In fact, even so, the point is, forget chemical bond. Even something older than this periodic table of elements predicted by Mendeleev, 150 years old, still requires change because of the new discoveries. So what people have found that these elements, as we know that as you go increasing from lanthanide across the F block element, the sizes of the ions contract. As a result, ionization potential of the elements should increase because now the electrons are much closer to the nucleus. Incidentally, as you go from lanthanide and actinide, as you keep on adding electrons to the F orbitals, you see suddenly just for lawrencium and lutetium, the ionization energy dips, which means these two elements do not probably belong to the lanthanide and the actinide series. So why are we changing it now? The problem was the lanthanide and the actinide ionization potential was not measured very well before 2 to 3 years. So only few years back we knew experimentally that the ionization, the first ionization potential of these two electrons, of these two atoms, are much lower than what they expect. As a result, they clearly don't belong to lanthanide actinides. In fact, now if you look at the ionization potentials of these two elements, for example, they actually fit more with the first D elements. For example, scandium, yttrium, lutetium, and lawrencium. So ideally, these two elements should be here, not in the F block. So in other words, lutetium and lawrencium should not be considered as an F block element based on this very recent experiment. Incidentally, in chemistry, that is the fun. There is always a theory which is already told that. For example, in 1929, the gentleman called Charles Janet had predicted a new form of periodic table. In fact, this is called the left step periodic table because as you go from left to right, your steps are increasing. In fact, he had said that lutetium and lawrencium should not be classified as an F block element, and they should rather be classified as a D block element. And this is what his periodic table 1929. Problem is, His model had to deal with the fact that he assumed that helium as an S block element. The problem with helium as an S block element in that case is you know that as you go down the group, your ionization energy increases. But unfortunately, as you go, you see helium to beryllium, the ionization energy should decrease. Fine. But then suddenly neon is somewhere here, and neon has a much higher ionization energy than that of beryllium. So as a result, we still don't have a very complete picture of the periodic table. We had always assumed that the 150-year-old periodic table, which is all well accepted, settled, and everything is done. No, we now have evidences that even our understanding of the periodic table needs changes. And chemistry is all about it. Chemistry is always a all moving, pervasive, moving concept. In fact, I would like to end up with this analogy. Anybody has heard of this gentleman called J.J. Berzelius? One of the greatest genius in chemistry. So what are his contributions? For example, he was the first person to say that compounds have stoichiometries, there are formulas. In fact, he was the first person to propose the formula for water, H2O. He discovered 4 elements: silicon, selenium, thorium, cerium. His students, PhD students, discovered lithium and vanadium. By the way, lithium is a very important element because all your smartphones are lithium. More importantly, his contribution to chemistry is massive because he has categorized, he has cataloged chemistry. He has given terms like catalysis. Catalysis was coined by Berzelius. Polymer was proposed by Berzelius. The word isomer, the concept of isomer, protein, allotropes of carbon, were all proposed by Berzelius. And Berzelius had said something very interesting. By the way, Berzelius is also wonderful because he wrote the first textbook of chemistry. First textbook of chemistry for mankind. And in fact, his textbook was called School Book of Chemistry. And in the introduction to the book, he wrote something very wonderful. And he said, the devil may write a textbook on chemistry because after every year or after few years, everything changes. Everything changes. So in other words, chemistry is an ever-evolving, evergreen subject. So you don't think that you have learned chemistry a few years back and that is enough. No, things change. The society changes. And as chemistry changes, society changes, technology changes, mankind changes. So finally, my final word of thought, the reason why I show a gecko here is, remember, the reason why I show a gecko because its color changes. And chemistry is all like that. With time, mankind, human concepts change. So finally, my own take or my own philosophical take on it is chemists or chemistry students or in general society must take time and analyze new results, new discoveries, new changes, and adjust accordingly. One should not stay forever inside the old framework and the old school and think that that is final. No, every day new discoveries are happening. Every day new technologies are coming. And in the society, in your future, this particularly to the students, only those students will survive and will thrive who are able to adapt to new technologies and new information. So please do not align to any particular theory, concept, philosophy. Don't. Try to have an open mind. Try to learn new things because that is why it will take you long fast. Because any concept will get outdated very fast. Be open and accept good things of life, good concept, but do not lose your originality. Keep your Bharatiya one, keep your Swarajya, and then get new concepts from the society. Thank you very much. Dhanyavad.
Thank you so much, sir. Thank you for the wonderful presentation. And you took us right from the copper age to the age of nanomaterials. It was wonderful to learn from your presentation. Now it's time to take few questions, sir. The first question is from DB Subanaidu. That what are the major factors that influence chemical bonding?
Okay. So chemical bonding is largely electrostatic interaction in largely, but then you also need to know electrostatic as well as laws of quantum mechanics. So it is quantum mechanics with the electrostatic potential defines the chemical bonding largely. Yes.
Okay, sir. There is a question like where we observe half bonds in chemical bonding.
It's a good
What
question.
do we mean by half bonds?
Half bond means where the bond order is half. One of the classic example is H2 plus. It's a very important molecule because this theoretically is a one electron bond because it is. In fact, this was used by Hitler and London to propose the one of the very important model of one electron. H2 plus hydrogen molecule where you have ionized one electron out. So it is H2 with only one electron. So it is H2 plus on the superscript.
Okay. Sir, the next question is it correct that the ancient Indian chemists used to prepare gold from the iron?
Okay. So the question is this: people have asked me this question about alchemistry. The people wanted. See, there are two things. One is it's true. People wanted to make gold from other elements. By the way, it is now even now it is possible to make gold from other elements, and you know how to do it. It is radioactive. You bombard them with high energy radiations. They will undergo change in the atomic number. Not a problem. Problem is nobody wants to do it anyway because that is far more expensive than to mine gold. The reason why this alchemistry is important because it's not that it produced gold, but by doing these experiments, people actually discovered a lot of new chemistry. For example, you all know that India was the only country which knew how to mine zinc. Nobody else knew how to mine zinc, and the technology was taken from India to UK. In fact, there is large evidence that this technology was smuggled out of India without any citation. In fact, people have drawn how to take. People visited the mines in Rajasthan, and I mean these are British who had visited our mines in Rajasthan, went back and then started the technology and deliberately killed the economy here. Thank you. Yes. Any other questions?
Yes, sir. The next question is from Apla Chakrabarti that should not be the member of F block. Kind question about it. Shall I repeat the question, sir?
Yes, yes. I think your voice is yes. Apala Chakravarti, what did she ask?
LU
Okay,
and
can you do it?
LR.
Can you write down on the chat box so that
Yeah, sure, sir. So can you read the question now?
yeah. Okay. So what she's asking is that the last part I said that lutetium and lawrencium should not be a member of the kindly clarify with literacy spectrum. See, the point is, this lutetium and lawrencium, which are the last elements of the lanthanides and the actinides, have been classified because their properties are similar, typically. So, but the problem is the recent experiments in 2015 published in Nature shows that the ionization potentials do not belong to that category. Ionization belong to the D1 elements. So, in fact, if you take into account that latest information, one would actually classify them as D1 elements under scandium and vanadium and not uh, under the lanthanide and the actinide series. I mean, it sounds outrageous, but then chemistry changes, everything changes. So what we believe as a concept will not be a concept anymore. Be acceptable, be open, keep your minds open.
Thank you so much, sir. And thank you so much to giving time to our Tuesday lecture series. Now, at the end, if you want to conclude anything about the session, so.
No, I think I had a wonderful time interacting with your team, and nice to see that the director himself sitting here in spite of his very busy schedule. And I hope all of you stay safe in Delhi. That is very important. And do take care of yourselves and do maintain social distancing because जब तक दवाई नहीं तब तक ढिलाई नहीं. Period. Please do take care of yourself. That is the. Please do that. Thank you. धन्यवाद. Unfortunately, Nidhi's net is having.
Thank you so much, sir. We keep those words in our mind. Nakul, sir, if you want to say something to sir. Nakul, sir.
Sir, mute. Sir, your mic is mute.
सबसे पहली बात तो ये आज हमारा 25वां व्याख्यान माला का पुष्प था. अच्छा सोपान, बहुत बढ़िया व्याख्यान, और लगातार नई नई बातें, नई नई जानकारियां मिली. और बहुत सारी चीज़ें ऐसी होती हैं जब आप कितना भी गूगल कर लीजिए, कितना भी कुछ कर लीजिए, जब तक व्यक्ति विशेष और विषय विशेषज्ञ इसके साथ न जुड़ के आपको बताए, तब तक उसकी रोचकता नहीं रहती. और हम सब चाहे कितना भी न्यू नॉर्मल कर लें, कुछ भी कह लें, कितना भी हम ज्ञान अर्जित कर लें, हमें हमेशा गुरु की आवश्यकता पड़ती है. और प्रोफेसर साहब हमारे साथ आज जुड़े, उनका अपरिमित ज्ञान हमारे को मिला. और सबसे अच्छी बात यह कि हमारे बहुत सारे लोगों ने ऐसे रोचक प्रश्नों के बारे में बात करी, हाफ बाउंड की बात करी, बहुत सारी तमाम चीज़ें. मेरा तो प्रोफेसर अयन दत्ता से एक छोटा सा अनुरोध और रिक्वेस्ट है कि इतना अच्छा भाषण है, इस भाषण को अगर आप एक छोटे से आर्टिकल में जोड़ दें, तो ड्रीम 2047 जो हमारी मासिक पत्रिका कम न्यूज़लेटर है, उसमें हम इसको जरूर छापना चाहेंगे. और ये बड़ा अच्छा आपका पॉपुलर साइंस लेक्चर है. इसका जो प्रेजेंटेशन है, इसी को अगर आप एक छोटे से आर्टिकल में, छोटा तो नहीं कहूँगा, जितना आप चाहें उतना लिखें, और ऐसे अगर आर्टिकल बदल करके आप हमें देंगे, अंग्रेजी में या हिंदी में, जिसमें भी आपको अच्छा लगे वो कर दें, तो हमारे लिए बड़ा सौभाग्य की बात होगी. तो इस आशय के साथ हमेशा ये रहता है, ये दिल मांगे मोर, जब प्रोफेसर अयन दत्ता मिलते हैं तो हमारी कोशिश होती है कि उनसे जितना ज्ञान अर्जित कर लें, जितना उनसे पालें, क्योंकि वो अपने हैं. और सबसे अच्छी बात है कि उनके साथ हम बेबाक तरीके से अपनी बात को कह सकते हैं. तो प्रोफेसर साहब, सचिन जी एक फॉर्मल वोट ऑफ थैंक्स तो करेंगे, पर मैं विज्ञान प्रसार, वेबनेट और सबकी तरफ से, विशेषकर अरविंद जी के अनुपस्थिति में सबकी तरफ से आपको बहुत बहुत धन्यवाद देना चाहता हूँ. बहुत बहुत साधुवाद इस बात का कि आपने हमारे अनुरोध को स्वीकार किया, हमको कृतार्थ किया. सचिन जी, ओवर टू यू.
Thank you, sir.
सचिन जी.
Uh, my voice is coming, I think so. I'm very much thankful to you, sir, for giving me opportunity to offer vote of thanks, because it's my honor that for vote of thanks I am there in this lecture series. Professor Andatta's topic is very catchy and very good for common men also, because it's chemical bonding and more surprises are coming on, regular surprises are there. So I offer my thanks from bottom of my heart to Professor Andatta for giving such their time and valuable time and energy in this lecture. And I also offer my thanks to all VIPNet members, because of them only we are able to organize this series for them, and all their relatives and students who are watching this lecture. After this lecture over, it will be available on YouTube also for watching later on also. So I thankful to the all the viewers who watch later on this lecture. I am thankful to my VIPNet team, Nidhi ji, Vipin and Pavan, and also of course my thanks to the director Nakul Parashar sir and Dr. Arvind Ranade for their blessings and their inspiration for organizing this lecture series. So thanks to all. Jai Hind, Dhanyavad.
Thank you. धन्यवाद.
Thank you, sir.